Welcome to Planarity. Planarity was designed for some of the most challenging healthcare problems that face mankind. Planarity is comprised of researchers, engineers, medical professionals, and most importantly, students. The primary design, the core design for Planarity-based MEMS, microelectromechanical machine chips, is the airfoil. The airfoil simulates, actually performs, a microscopic nanoscale wind tunnel that operates on fluids that contain particulates of various sizes, such as is found in cancer pre-detection using flow cytometry. In the last 2 years, over 12 patents of intellectual property have been filed in the field of acoustic focusing as well as hydrodynamic focusing involved in flow cytometry. The goal is to create a single stream of individual particles in the biofluid which will pass through a Coulter counter. These individual particles are not random. They occur along a straight line and are of varying dimensions. This to be able to indicate to a clinician the size and the pathological content of each individual cell, such as is the case in metastasized cancers. Planarity takes a different approach. We have reason to believe that aerodynamic structures, which are dimensionally scaled in close proximity to the size of molecules in the nanoscale regime, are capable, even at picomolar concentration levels, of differentiating particles, molecules, contents of biofluids, as is found in flow cytometry and cancer pre-detection technologies, and to be able to do this in a trellis which performs an algorithm. Each airfoil bifurcates the stream into high and low mass categories by design. The first level or tier in the trellis bifurcates into 2 resulting streams. The next subsequent tier into 4, the next subsequent tier into 8, and binomially until each individual molecule or cancer particle is separated into a particular bin or category. And this represents a form of mass separation. The basis of this is a design many years ago which validated the theory of the gas centrifuge for separating uranium-235 from other isotopes of uranium, mostly for the purpose of warhead production. And the patent was given to the South African government, and it employed something particularly known as the Becker nozzle, which performed aerodynamic separation of gas-based uranium-containing isotopes. This is known in the field as a stationary wall mass centrifuge. The aerodynamic properties of an airfoil do something very similar to what is known as hydrodynamic focusing. Hydrodynamic focusing involves the injection of a secondary fluid, not a sample fluid, but a secondary fluid coaxially about the sample fluid. This introduces an artificial slip boundary layer, and the particles are then constrained into a narrower focus, almost like a rank and file if it was down to individual particles or individual molecules, one after the other, as they are then driven into a Coulter counter. Our technology is mass producible and makes use of the large-scale implementation, not just of the trellis and not just of the algorithmic relationship of one airfoil to a field of airfoils, but similarly to an integrated circuit. The entire logic, if you will, fluid logic chip which we are proposing is driven by a high-speed impeller. Such has been demonstrated by the University of Maryland under contract to the U.S. government, and the prestigious Nanotechnology research group there, which was able to accomplish a ball-bearing, coplanar, dual sandwich structure in MEMS, in monolithic or planar technology, that rotated at approximately 85,000 RPM. This is enough speed and to be able to impart enough velocity to the biological fluid to develop, albeit self-focusing, artificial slip boundary layers, which can hydrodynamically focus particles into a narrow, very narrow, one-cell wide stream. We at Planarity are very interested in using nanoscale airfoils for mass separation as well as to perform logic on fluids. We are presently modeling our technology using multiphysics simulations and solvers, and are working with the famous company ComSol, who has graciously extended us a trial license for their multiphysics simulation package, where we use the acoustic, the plasma, computational fluid dynamic, and aerodynamics packages, simultaneously solving for all four regimes the phenomena that we represent as our technology in our trellis of airfoils. Furthermore, we are looking at other applications of our technology to biosensors, which involve the detection, the rapid detection and discernment of pathogens, such as is found in biowarfare.